Today, I want to talk about concurrency and parallelism and some real life development. This, of course, is in the context of event sourcing. We'll talk a little bit about from the perspective of a consumer of an event sourcing system. And I want to dig into some of the ways we've taken advantage of parallelism as a tool maker trying to build event source systems. So just tiny bit about me, even though it's a duplicate. I will try to casually scan Twitter while this is going on if you want to ask questions that way, but more likely I'll probably miss it. We're going to talk a little bit about a tool called Marten. My part of that, I'm the lead developer of Marten and one of the co-founders. And there you can see where to find me on Twitter if you want. Just to give you context, because I'm going to talk about both using Marten and some of the building of Marten, just to kind of catch up for folks that aren't familiar with it. This is an open source library in .NET. It's been around for about 5 or 6 years. We just actually have a massive new release about 4 or 5 hours ago, just in time for this talk. So Marten sits on top of PostgreSQL. It's just really just a library. It allows you to use PostgreSQL as both a document database and also as an event store. And while using Marten as your event store, the document database feature, that's conveniently enough, that's your read side projection storage as well. Specifically, I'm going to do a deep dive into the asynchronous projection support that we have in Marten today. Marten comes with some out-of-the-box, completely in-the-box projection support that's meant to be usable without any other additional infrastructure besides Postgres itself. So no event streaming, no Kafka, no Pulsar, no nothing else, just a constantly running process within a .NET application that can be constantly scanning and applying events to your new projections. And like you said, yay, we got a 2 years and counting release out just today, our big V4 release. So we have been calling that our Duke Nukem Forever release, and it's finally out. All right, so things I want to worry about, just one more time. Let's put ourselves in the shoes of a user. What do we need to worry about with concurrency as somebody who's building an event source system, and maybe some of the tools and approaches we might make? And then I want to dive into the making of our asynchronous optimization. Assuming there is time, I want to talk just a little bit about some of the challenges of testing a system like this that has a lot of asynchronous parallelization and concurrency, and how to make tests be a little more reliable. Okay. For a sample system, and I'm assuming that most of the people on this call are probably pretty familiar with event sourcing to begin with. I'm going to talk in the context of a contrived system we actually built for testing. Let's say that you are taking a road trip, and be clear, you're taking a road trip inside of the continental United States. So we're going to talk about states versus a province or a country. So in the side of this road trip, you may be recording events like a trip started, a trip ended, a trip was aborted for some reason, and just tracking, hey, we traveled so far on a certain day, starting in this state, ending up in another state, we drove this many miles. But then partially, there may be contracts and events like we broke down, right? On the right side, there's a couple view projections we've rigged up. One is just we're calling a trip. It's a state of an individual road trip, an individual stream of events, closely related events of a family leaves on a road trip. How far have they gotten? Where did they start? What day are they on? Where are they now? Right? And as another possible projection, really, again, something that's just made up for testing, we have a projection model we call a day, just allowing us to say for all the active trips out there, how far did everybody drive in what state within a single day? Okay. So just looking at a diagram of the system a little bit, what it may be like. So we have a bunch of users, a bunch of travelers, and they're constantly recording updates recording their progress, recording when they start. And that's going to be some kind of recording service that's constantly posting events to the trip database. Now off to the side, or maybe not off to the side, and I'll talk about that more, we have a constantly running process we call the async daemon. This is our asynchronous projection engine, constantly updating these events coming in and creating views and aggregates of all the trip data that's available for the administrators of this system in a trip process viewer. You see that up here. Okay. Now, let's dive into the potential problems. The first is we need to be concerned about concurrency. The reality is that multiple family members may be sitting and pounding on the app and trying to update the trip at multiple times. And if they do that, there's a good chance that, say, if we're on a trip and my wife and I aren't communicating too well, not that that ever happens in real life, but we're not communicating very well. So she enters the day's entry log of progress on one side while I'm doing the same thing off to the other side on my phone. There's a heavy potential here that our two progress reports, if they go in at the same time, they could easily make the system be in an invalid state. We've captured wrong data. That's an example of concurrency. And parallelism. This is just the idea that you purposely set out to take advantage of multiple cores on a computer or multiple threads and purposely break an aggregate of work into discrete tasks that can run in parallel with each other. So as we walk farther into this asynchronous projections, we'll talk about how on Marten we try to use parallelism to try to speed things up. It's coming back to our system now, but let's identify some potential problems. So we know as we're recording updates to a trip, we have potential concurrency issues. Right? And we also know from 5 years of supporting Marten that our asynchronous daemon, the asynchronous projection engine, we knew that it needed to be much faster as we just did this massive V4 before release. And one of the ways in which we tried to drastically increase the throughput is try to utilize a lot more parallelization within this daemon. And I'll talk about that. First, let's worry about this. Okay? So, hopefully your events and your streams, however you're aggregating things, hopefully it's very unlikely that you ever have one person or multiple transactions hitting the same stream at one time, but it certainly happened. I've helped support systems that had this problem. So we need to be aware of that somehow, and we may need to do something to enforce that a particular stream is only updated once, or that you're not applying data to a stream that's no longer valid. Okay. So we'll take a look at that real quick. I'm going to switch to code finally. And let's take a look at that. Okay, so the very heaviest way we could do this, Marten being on top of a database engine, Postgres in this case, if we really wanted to, we could do this in a super heavyweight way. We could actually use serializable transactions so that whenever anybody tries to update a trip of a stream of any kind, every request has to go in single file, right? That's obviously going to dramatically impact the performance of your system. It's going to slow your system down quite a bit. And it still doesn't completely protect us from somebody passing in progress at the same time if they just happen to get first. So we don't want to do this. This is at the database level. This is at the event store itself level. Let's not do this. Another possibility is to, as we record, now this is MVC, I should have explained. This is an MVC core controller. Let's say this is just a made up endpoint that's going to receive some kind of progress about the trip. and update the event stream. So walking through it a little more slowly, I'll come back to this. We look at the existing trip, look up the aggregate for that. And from that basic trip, we can take a look at some of the events. We can figure out what events we need to process, based on today's progress and the existing aggregate. Did we arrive in a new state? How far did we travel? So on and so forth. And finally, we can append the events and persist everything inside of one transaction. And I'm going to come back and talk more about transactions in a minute. What I'm doing up here is what we can effectively do here is lock at the stream level, not at the event store level, but as a way to control concurrency, still heavyweight, but without the serializable problem we had before. We just say, hey, I have exclusive rights starting here to be the only person who can append to this stream. And when I do this will actually wait until it can achieve the lock, or it times out and the whole thing blows up. Okay. This is a possible approach. This might be helpful. Still it's heavyweight and still not the most awesome thing for performance. So dropping back, again, I'm thinking as a user, what are the tools in my disposal? Lastly, we can go to using optimistic concurrency. And what we're doing now is assuming that at the time that we recorded the progress from our little user interface on our phone, that we were looking at a certain version, at what we thought the current version of the trip is. That we've made these additional updates, assuming that the trip is exactly at this place. And when we issue our updates, it's a little funky usage, but we know that, according to Marten, that the current version of the trip aggregate that we're editing, we think it's this version. So let's say we think we're editing version 10. And we pass it up and we tell Marten, I want you to append new events to this aggregate in this event stream, but I want to assume that the starting version was 10. And that's actually what's happening logically here. When this is saved, as Marten tries to append the events to the stream, if it sees that, no, somebody got in between you and the actual current version of this particular trip stream is 13 when you thought it was 10, this will reject it. This will reject it with a certain a specific exception, which you could handle. You could do retries, but you could handle it back at the client and say, hey, somebody has updated this in the meantime. Would you like to refresh your screen and start over? So this is using optimistic offline concurrency here. This is a pattern that will allow us to still guarantee that only one person is editing at a time, but we can do this in a very lightweight way and only ensure that it hasn't been edited at the point that we try to save. This is faster. It's a little more work on the developer side to make sure that you're collecting the current version and passing that back up from the client to the server side. But it still comes off with the trade-off of this is more performant. So if you think that concurrency violations are going to be rare, go with optimistic concurrency. If you think it's going to be very common, then maybe you go with some of the heavier weight approaches that try to lock it. And as one of the developers, part of the core team, Marten, we just tried to make sure that the users of our tool have choices. This has been something that's been one of the goals of our most recent release. Yeah, sorry about that. Absolutely, we'll make the font bigger, and I'll make the font bigger as we go. Okay, couple more comments on this. Then our next thing about concurrency, something maybe a little specific to Marten, but the projections. If we are tracking and constantly building up that trip aggregate from our from our events, we actually have the choice in Marten. We can say that the trip will be built completely in line. And what we mean is at the time that you're capturing new events for a particular trip stream, as you try to save the events, we'll actually go look up the current version of currently persisted version and apply those events to the aggregate right then and there and make that be part of the unit of work. So you get a strong consistency model. Okay? That's extra overhead as you're appending events, so it's always a trade-off, but it does give you that model of strong consistency. It gives you ACID, transactional integrity between your read side view and your events. It's something that some people may like. That's possible when your streams or your projections are unlikely to be impacted by concurrency, which of course, sometimes they are. So your other model is just to decide, should I instead make this be an asynchronous projection and opt for eventual consistency and let the background process constantly try to update my read side projections as I go, such that I can optimize my event capture. They can move faster because they don't have all that extra work. I dodge the concurrency issues of potentially colliding on multiple processes trying to update the exact same aggregate projection. And I got a little bit of a trade-off there, but it allows me to work. Just making this a tiny bit concrete. You go back to the code just a little bit. So show what the aggregate may look like. And it's real simple, real crudely. You know, this is actually the stream ID in this case. Just tracking, do we know when the trip ended? And our simple calendar system in this test system is saying that the first day of the system is day 0 and every other day is an additional day. So we're tracking, when did the trip start? Is it completely active? What state here? Is it in, I'm in Texas? Is it in Ohio, New York, wherever it happens to be, assuming that the world completely ends at the borders of the United States. Okay? And an aggregate of how far did it travel? Again, trying to make just loosely, seeing how some of the projection is going to be applied to this trip. You see how we are applying a few of the events. Again, this is test code. This isn't even complete. Tracking your arrival. How do we mutate the trip aggregate? You see how this goes. Now, in terms of registering the event, or registering the projection. So, you know, hopefully everybody who's at least a .NET developer, this is the idiomatic way to bootstrap more recent .NET applications, or at least a web service through the startup class. So add Marten. This is where we're just adding Marten into our applications DI container. I was going to tell it where Postgres database is, but at this point, I can say, do I want this trip aggregation that's creating this projected trip view? Do I want this to run inline with a strong consistency model, but knowing that appends are heavier weight and there's possible concurrency issues? Or I can instead put this in the background and make sure that I'm actually running the probably help if we made sure that asynchronous projections are actually running. Not to go too far in the weeds here with Marten, but what I'm doing here is saying I want the asynchronous daemon to run on one application node, and it'll deal with leader election and failover and everything else like that. As I'll talk about in future plans, we don't have any way of running splitting projections across multiple nodes, but that's an obvious way to obvious next step for us with Marten. Okay, so just kind of reviewing what we just learned or what we just looked at. paying attention to concurrency and also consistency models that helps us choose whether a projection, an aggregate projection, should run inline or asynchronously with eventual consistency. And we've also looked at lighter and heavier methods for controlling concurrent access to our event streams. Any questions on that before I move on? And we do have a Q&A session after this. All right. Now, to the harder problem, processing our asynchronous projections. Events are constantly flowing in. Let me show a quick sample here. Okay, I'm going to run two different applications in 1 second. Before we do that, let's actually have a database to write to. 1 second. Okay, so brand new Marten data Postgres database, really brand new Postgres database. So I'm in one application. I am going to run this little command line thing. All this does is continuously spawn and write random events towards trip aggregates. So you see a whole lot of text flowing through there. So now we have a whole bunch of events running in through the system, running into the database. Now on the next side, just a little helper. I'm going to not run an entire application. I'm just going to run the application with projections. So Marten has some optional add-on command line support that you can add to your existing application. And one of the things it will allow you to do is start up your application, but in a lightweight way, but only run the asynchronous projection daemon. And that's what I'm going to do here. And this worked 5 minutes before the presentation talk, so it should work right now. So we're going to compile, we're going to start up. And it looked cleaner before. We're a little messed up, but you can see the process here. Right here. This is telling us the high water mark. This is telling us how far the event store itself has proceeded, or at the safe point where projections can work from there. And there you were just seeing some of the projections that are attached to the system, where they are right now. And you can see in this case, they're actually able to keep up. This is a super lightweight projection. That's kind of cheating. Still let it go. Okay. It's off. Another problem. So for those of you who've already built event source systems, you're very well aware that sometimes the projected view changes, right? And there is some reason why you need to rebuild a projected view based on the events and do it now from scratch. Okay, so I'm about to do that here in a second. But this is a place where you obviously need very, very good throughput. You need this asynchronous projection engine to be much faster. This is a big complaint that we had with Marten. So let me show you what it is and show a little look and feel so far. This is just to establish what our problem is, maximizing and optimizing the throughput of this process. You can see some of these are faster or slower. So when I ran this, what it's doing is it is wiping out the storage for all of these projected views. It is rewinding them back to 0, saying that progress is at 0, and then just running the projection engine all the way through until it catches up with what it knows to be the furthest point of the event store. And that's it. Okay. So this is where we started from Marten v3. This is where we were until about 5 hours ago. So inside the hood of just in this case, let's only think about a projection, the trip projection, that is taking all these related events, trip started, trip traveled, trip ended, combining them up into what is the current state of one single related trip. Okay? When this is running in the background, these are the logical steps that are inside the Marten asynchronous daemon. It's we process things in batches, and that's very important. Being able to process things in batches enables us to be more efficient about how do we go out and find the existing aggregate state that we need to update. It's much, much faster to do that in minimal round trips. Kind of a mentor to me who might possibly be on this call used to always say network round trips are evil, with this idea that performance optimization is all about trying to avoid being chatty, making too many network hops. So that's part of our thinking in asynchronous daemon, and performance optimization work and benchmarking definitely proved it out anyway. So we try to fetch a bunch of events at a time, and out of those events, now, all the events we take off, we need to group them by the streams that they're part of. What trip are they a part of? Because we're processing this particular type of aggregate one trip sequence at a time, one trip stream at a time. So we have a process to now take the whole stack and then group them up so we can work on them group by group. Once we know what all the groups are, we know all the unique trip IDs that are part of this page. Then we try to reach out and grab all the existing aggregates for those trips all at one time, right? This is another place we want to reduce the number of network round trips. So being able to batch a query is very important. Now, for every single aggregate, and I'm going to drop back to the code just a little bit again. Just to make this clear. We're running through every event and we're determining what's going to happen to the aggregate. So if it's an arrival, we update the trip state. If it traveled a certain amount, we're going to append, we're going to add on the running total of how far have you driven total. If it's ended, we're going to mark it as it's done. There's other things. We may even decide to delete the trip out of the current system. Maybe it's been aborted. Maybe you broke down and whatever the mechanical error is, it's critical. It can't be fixed. Game over. You're done. Wipe off the trip out of the active trip category. Okay. So the point being, we've got some work to figure out what to do for every aggregate. In the internal model in Marten, that's something called an iStorage operation. And part of an iStorage operation, this might actually be useful to see. Now, this is kind of ugly in here, but this is the key part I want you to kind of focus on. These storage operations, one could be update a document, insert a document, delete a document. But all of these things are going to write a little bit of SQL to a big aggregated SQL command. So that's what we get to right here. So again, if we want to be fast, what we have measured consistently is Postgres behaves much, much faster if you can send a batch of commands rather than trying to make individual round trips. So if we're updating literally up to 1,000 trips at a time, maybe not that many, we want to create only just a handful of batch SQL commands and send the whole thing up at one time. So all the storage operations are coming through, and all of those turn into a little bit of a SQL command. In this case, it's actually executing generated Postgres stored procedures. I know that's a dirty word, but just let it go. So building up this big batch SQL, and part of it, everything that Marten stores, all projected documents, all events, it's all serialized JSON sooner or later. So as it's working, it's constantly serializing JSON and stuffing the JSON bytes into an ADO.NET parameter as part of this command. The point being, this is actually pretty expensive to build. All right, it's a lot of string manipulation. There's a lot of JSON serialization. And lastly, once the command is completely built, it could be more than one command if it's really big. But once all these SQL commands are built, now open up a new connection, execute it all, do some post-processing checks for optimistic concurrency, and be done with things. Okay? But this execute can't happen until all of this is done. Okay. So now, to make things faster, and this was already in use with V3, but I think we got a lot smarter in V4. We're going to introduce the producer-consumer pattern. It's a concurrency pattern where a background thread or process could be constantly kind of working and creating work for downstream consumer threads. And you do this when you can't perfectly parallelize work in concrete steps. But what you maybe can do is parallelize some of the preparatory work before the execution. And I've always found this is mostly valuable when maybe there's some kind of sequencing rule where a resource cannot be accessed concurrently. In this case, now showing you what we're doing now, there's places where we can and cannot do parallelization, but down at this execute, this can only be executed one at a time. This has to be single file. Running a projection, as I'm sure you're aware, we need to run perfectly in order. We need to be running pages of events, but in exactly in the right order. We can run 0 to 100. We cannot start 101 to 200 until 0 to 100 is finished. So some places we have to be single file, but other places maybe we can do some parallelization. But what we can do, just logically here, is in a background process, we can actually be fetching event pages at a time, ahead of time. And we can have them kind of queued up and maybe eventually start to have them batched up, right? So that's a producer, this fetch next event page. So this is constantly working and making sure that it's so many events, at least so many events ahead if it can be. It is a kind of a pool-based model, so it'll stop if there's too many things in the queue, so you don't blast your memory, of course. Beyond that, kind of moving down to another activity, we could be in page by page. We could also be grouping them ahead of time in this case. So this is just saying, I have 500 events over 10 different trips. So I order those and group those by the individual trips, so it's ready to go. And we can do that work ahead of time before anything else happens. But we do know, since we are dependent upon existing state, we cannot start any other work against a page of events except at this point. So once we have a group, this box, this dotted line block, this is a logical operation of here you have all these groups, now go update the aggregates. This can only be done one at a time inside of this. But even in here, there's some things we can do. So the logical things we need to do is go find the existing aggregates for the trips, if they exist. In some cases, we can tell that a trip is brand new. If the first version event is 1, we know that, hey, this is brand new. So we can actually skip fetching. We can let those dribble in one at a time and have in parallel, we could start running the updates. So this determine update action, come back to the code, try to make this a little bit clearer again. Back to the trip. So that is running through this class right here. This is applying, it's doing some pattern matching against it, running all these events through, figuring out what to do with the trip. Is it updating it? Is it building a new one? Or is it marking deleted? But we can actually do this in perfect parallel. We can let this happen for every individual trip. This could be running in parallel. And as I'll show, that's actually what we do. The SQL command, that big batch SQL command, there's JSON serialization, it's kind of expensive. So it'd be really nice if we could let things happen ahead of time. And as soon as an update operation is determined, let it immediately start applying its changes to the SQL command building, even before everything else is done. And finally, all of these logical things have to be done. The SQL command has to be complete, and then you can execute the database transaction, and then allow another group to be the next group to filter into this dotted line box. Okay. We'll call out, just as another concurrency thing, I kind of mentioned as an aside that we have leader election for the async daemon. Right now, there's a limitation that only one async daemon can be running at a time. But, I mean, users do funny things. It's real easy to accidentally spin up two in parallel to make sure you're not getting invalid results because you have parallel async daemons. There's actually a little bit of optimistic concurrency right here at this spot, that when it is applying a batch of updates, it's also saying, I expect the current progress for this name projection to be at spot 1,000. And when it does this, if it sees in the database that something else has somehow advanced it to 1,500, it will fail this batch right here, and it will actually make the projection stop and potentially restart from the point where the database says it is. You know, that can honestly cause you worlds of contention if you really do have two things running at a time. But at least this is going to stop you. This is something we added in V4 to stop the system from getting into an invalid state. That's another example of some optimistic concurrency protection. Okay. For the .NET folks in the audience, we're heavily using the TPL, the Task Parallel Library data flow components. So this is something that Microsoft's built. I don't know if it's very well known, but we found it to be very helpful, and I've used it in other projects, both in open source world and now in some of our meta-analytics work. It's been very helpful for us. So this allows us to kind of model the world in execution blocks, like a stream of data and processing, but also define what is the maximum concurrency for any of these blocks. So we can have a mix of blocks that are completely single file. You know, for places like the event grouping, everything has to be processed one at a time. It cannot flow out in parallel, or like determining the aggregate per group. We can actually let that to run in parallel, and these blocks can also be chained to each other. So now let's look at the internal designs. So internally, there's something called a shard agent. Think of this as the logical controller for a particular projection. We call it shard because someday in the future, we will find a way to have parallel processing of a projection where we can find logical breaks. For right now, single file event fetching block. This thing is going to keep passing in page requests. Hey, I happen to know that we could start a new page from 0 to 1,000, 1,001 to 2,000, so on and so forth, and send these requests in. One at a time, the event fetching block will reach into the database and go grab the next set of events. So that's reading through a database reader, doing a lot of deserialization, creating .NET objects, then handing that off. That's linked to a single file block that can do the grouping. So the grouping can take 1,000 events and group that into 10 trip aggregates or whatever it is. It's not building the aggregates, it's just lining them up in a group so they can go into the next block, the processing block. So this is where one at a time, again, take all these grouped events and then actually process them. This is a place where we can do a little bit of parallelization. So each individual event group, which should correspond to a single trip, that can actually be processed somewhat in parallel. The things that are CPU bound, especially, let them do that. And then it's going to chain all of their storage operations to a SQL building block. This goes one at a time. So each block can be running and serializing the aggregate document to a parameter, building up, appending to the SQL string. That's all done through SQL builders because we're doing a ton of string concatenation. You can also see where that SQL creation that obviously has to be done single file. You cannot have bits and pieces of totally unrelated SQL commands getting written to the string builder at the same time, or you get all kinds of weird syntax errors. So this is all single file. But inside the processing block, it can spawn up new tasks for all of these things. Well, actually, in reality, they're just little blocks. All these blocks can be running. The event groups update. Single file gets processed inside the SQL building block. When all of these are complete and all of these are complete, it finally gets to go execute the SQL command against the Marten database and then allow another group of events to come through and be processed. Okay. So this is what we've done so far to try to do more parallelized work inside of our async daemon. Take advantage of having multiple cores, but also take advantage of any possible way we can let CPU-bound work proceed while we may be waiting for other work to go out and reach into the database, but to make sure things are not single file. In future, and this did not make it into our big V4 release, one of our ideas is take, like this logical trip collection, maybe take advantage of multi-tenancy. Maybe we could say even shard up a projection over part of the stream and say, we're going to run a completely different projection shard for the trip for tenant A versus tenant B versus every other tenant. And so that we could start spreading the work out and let these projections, the same projection, work over part of the event store, but on different nodes. That's the next frontier for us in Marten as we try to grow up into bigger and bigger systems and more scale building. Okay. All right. So all this asynchronous daemon stuff. We also have to test it. We have to test the async daemon ourselves before we let any users use it. But then as you're a user and you want to test your own projection running in this async daemon, how are you going to do it? What's frequently happening is you are doing some kind of activity that's happening in a background thread from your test harness. But to make a test be reliable, you need some way to wait until you can check your assertions. So going back to the idea that any kind of test, it's the arrange, set up all your inputs. Act, in this case, would be run a bunch of events through the asynchronous daemon, and then finally an assertion. But this assertion can't happen until all of your events have actually gone into your projection and run through asynchronously. Okay. With Marten, you could flip it and run your projection inline only in testing, just as a way to make things be more predictable. But still, let's just assume you have to do it asynchronously. So from there, I want to just talk about the internal approach we use to test this for ourselves, which is also going to be available to everyone else. So this is a test inside of our asynchronous daemon testing code, just to prove out that we can run an aggregate with a bunch of events, and it does what we think it's supposed to do. I won't get into too much to our custom test library, but we're running one shard, so we know what that shard name is. We know, in this case, how many events should have been published. So that tells us, starting from an empty database, this is the high water mark of this particular projection we want to get to. So we actually built in, using iObservable, we actually built in a system where we can constantly listen and publish events of how far the async daemon has gotten on each projection, or the high water mark out to iObservables, and use that to wait. In this case, we can set a condition, wait for this particular projection to get to exactly this point, and give it a timeout, because there's always a possibility this could not work correctly and run out of control. So you have to have a timeout to detect that things fail. Looking inside of that. So this is all this is just a fancy way of knowing I want to wait inside the tests until all of our processing that we expect to happen is happen inside of our daemon and all this background threads. Just looking at mechanism here, going a little behind the side. So this is possible to do with, you could rig up something on of your own on Marten, but this is built in. Hopefully you can see here. So we're using the iObserver pattern or the iObserver mechanism in .NET. We purposely built the async daemon to be pumping events anytime a shard is, in this case, part of a projection. A projection is advanced successfully, or failed, or stopped, or started, or paused, or whatever it's going to be. But anything that it does, it's pumping out an event called shard state. You see just a little bit of what it's tracking. What's the name? How far did it get? When did it happen? A little bit of information about failure cases. In our watcher here, we spawn this up. I know other people have done, I've seen other people do this different ways. I like to use a task completion source. And this is what's actually getting returned in the test engine here. So this line of code that we're using to wait on the process, this is actually the task of a task completion source. Just giving a chance to say stop until this thing is completed. Inside this tracker, every time this tracker is updated, it's trying to talk to this guy in our subscribe here. And if it is detecting, sorry folks, it's been a day or two since I've looked at this code. So if it's finding, like in this example, if it's finding that we have received the place we want to, my apologies, folks. Yeah. So as it's receiving new updates to the shard state, if it determines that the condition I'm looking for, this particular shard state, this particular shard was supposed to reach 1,000. If it can say, yep, my condition is fulfilled, I'm going to mark it as my task completion source as complete and get out of there and unregister myself. But all that way back here, this is just allowing our test to reliably wait until the async daemon advances exactly as far as we wanted it to go. So this will help make our testing be more, our automated testing be more reliable with all this asynchronous processing. As opposed to trying to say, you know, what you don't want to do. If any of my coworkers ever watch this, they know that I should know by now that I would yell at them. Not actually yell, but the thing you don't want to do is say like some kind of hard-coded, I want to just pause for 10 seconds and let things happen. That's setting you up for a race condition inside of your automated tests. Make sure automated tests be not very reliable, makes them flaky. Instead, you want some way to more reliably wait for, when do I know I can go check things? So also make your tests, potentially make your tests be faster as well, because you're not waiting too long. You're going when you can. So I put this in here because automated testing, this is something that's very important to me. This is something I want our users to be able to do themselves and do reliably. That's why that surfaces in Marten as a first-class citizen of our design. Okay. And honestly, I think I'm about right on time, or maybe a little bit early, but at this point, I'd like to just open up for questions.